Okay, so on to the subject matter. If you have material that's causing you a real problem and you don't know how to characterize it, then we have the expertise combined with the analytical techniques to help. Today, we're offering you an insight into some analytical techniques that can help you with finding a solution to your problem samples. Next slide, please. We analyze many types of samples using a variety of techniques with a vast array of equipment. Today we'll focus on 3 of those techniques and with respect to characterizing problems and providing scientific solutions. These are Scanning Electron Microscopy with Energy Dispersive Spectroscopy, SEM EDS, Fourier Transform InfraRed Spectroscopy, FTIR, and X-Ray Powder Diffraction, XRPD. And you can see now why we use the abbreviations to highlight these techniques. Next slide, please. These 3 groups have long been established at the Institute, and their strength comes from not only being under one roof, but also from the high level of experience and expertise in the scientists that lead them. Today's webinar will take you through the technical aspects of these analytical techniques and the materials they are applicable to. It will be presented by 3 of our experts who together have over 100 years experience in their fields. They will demonstrate how to use their techniques either individually or in combination to characterize most types of samples and answer the majority of your requests and questions. Next slide, please. The 3 experts you're about to hear from are Evelyne Delbos for SEM EDS, Jean Robertson for FTIR Spectroscopy, and Steve Hillier for XRPD. The presentations will run back to back, and I will collate questions and submit to the panelists at the end. Please note that the slides are numbered in the bottom right-hand corner for your convenience should you have a question on a specific slide. And I will now hand you over to Evelyne.
Yes, good morning, everybody. I hope you can all hear me correctly. I will definitely explain to you a little bit of the scanning electron microscopy as I lead this suite. Next slide, please. So you may have some material of any type that is really causing you some headaches, and the best way to characterize it may be a little bit obscure. So what is very important to remember is that the question you have about these materials will actually define the technique that we will be using to answer your question. So really keep in mind that question. Next slide, please. So what do you want to know, or what may you want to know about the material? It might just be simply, what is it? What kind of material is it? Or is it, can you do some kind of qualitative determination of the composition? But you may have on the other side a very specific question about it. It could be that you want to know a very precise composition of it. You may want to know whether there is simply a particular compound that is present or absent within the sample. If you have a rock sample, for instance, you may need to know the pore space size, the distribution of it, or the morphology of the minerals around it. How is it interacting? In a liquid, you might want to know whether it is a pure liquid or whether there is a contaminant into it. If you have some kind of emulsion, it might be interesting for you to find out the size of the droplets and give you some kind of insight of why that emulsion may be stabilized. Sometimes you may also have some rubber seal, for instance, that have been damaged, and you might want to know the state of degradation of these rubbers. But in any case, whatever your question is, whatever you want to know, you need to be keeping track of the question and in what context it was asked. The reason for that is sometimes it can be difficult when you have a chain of subcontractors from the originator to the final analyst, and the question that is being asked is kind of lost, or the context in which it is being asked is lost. For example, a sample of produced water may have been sent for analysis with a request perform FTIR analysis. And there are some solids in there, but there are obviously a lot of liquid. So what was it that the originator wanted to know? Was it because they wanted to know the composition of the solids, because they were causing blockage, and they needed to find out the reason? Or was it because you wanted to know whether the liquid itself had, for instance, a lot of oil in it, or whether there was a contaminant? So without knowing this, when it passes from one contractor to the next, it can be that we perform an FTIR analysis, but the results are probably possibly useless if we have not looked at the proper part of the sample. Next slide, please. So what type of material can we have a look at? Obviously, the solids and the liquids, and that forms all the different types of materials. All the solids are geological materials, obviously, and other types of all sorts. And within the liquids, there are certainly the oils and the waters. Now, in between the oils and the waters, you have also the emulsion, any mix of it, and add the solids into that, and you do have the sludge that are causing so many headaches to the oil industry, but also other industries as well. Next slide, please. So SEM and EDS, electron microscopy, this is the suite that we have, and we do have basically two instruments in one: the Scanning Electron Microscope, SEM, and the energy dispersive spectrometers, the EDS spectrometers. Next slide, please. So the SEM has got this column, and that emits all the electron beam to bombard the sample. And in our system, we also have two EDS detectors. And we also have the chance of an attachment, which is a cryogenic unit that allows us to do samples on a frozen state. Next slide, please. So how it works, very, very briefly, the column emits a beam of electron which goes through a set of apertures and coils and condensers, and the beam is scanned across the sample, which in turn emits different types of signals. Amongst these signals is different types of electrons. Those electrons are collected by the electron detectors and processed to generate different types of images. In this case here, we can see topographical images that can be done on organic material on the right-hand side, and on inorganic material when we have rock samples with different types of minerals on the left-hand side of the image. But these electrons are not the only signals. Next slide, please. And we can also detect some X-rays that are emitted by the sample itself as a result of the bombardment. And the X-rays are processed by the spectrometer, which produces a spectrum of different elements. And these elements are not a compound. They're not giving you exactly what the chemical compound is. It tells you what elements are present inside the sample. So this is important there, because we'll see the difference with the two other techniques, which can determine exactly the identification of the material. Next slide, please. So capabilities of the SEM is essentially qualitative. We can produce images of the surface topography of the material, like we've seen just earlier on, but we can also produce different images. One image using the backscatter electron is called a compositional image, because it gives you some more indications of the density of the material. For instance, the image on the left-hand side is a sample of sand, and the grains of sand are mostly gray. But the very bright material is steel, and that steel has a higher atomic number, and therefore in backscatter for the compositional imaging it appears brighter, whereas anything with a very dark material with carbon, for instance, is appearing very dark on the image. We've seen that we're getting also the elemental composition by the spectra, which we've seen in the previous slide. But we can also combine the compositional imaging and the element mapping, the elemental composition, excuse me, to make mapping of the different elements, and we can find a distribution of all the different elements. On the example that we have here on the right hand side, we do have the combination of copper, titanium and magnesium on this imaging. Next slide, please. So that was a qualitative. We can actually do quantitative elemental analysis of material, but it has to be done on very, very flat surface so that we can actually know the exact geometry between the sample and the detector. So polished surfaces are absolutely essential for quantitative. The types of samples we can analyze are very varied, obviously. Anything that is solid can be looked at. But as I mentioned earlier on, with the cryogenic attachment that we have, we can also look at semi-solids and liquid samples, obviously in a frozen state, so they become solids. The sample size of the material is also very versatile. Anything from 10 centimeters in diameter down to less than a micron is possible. Next slide, please. So if we place our samples into these triangles that we have, essentially the solids are the main type of samples that we're going to be looking at, a lot of mineralogical and geological samples, but anything else, we have done many, many different types of analysis on metals, on polymers, ceramic, and anything, and obviously microfauna and flora with the people we're working on here. But with the cryogenic stage, as mentioned before, we can do anything from the liquid samples with the emulsions, any suspensions that would be within these emulsions, and sludges, and more importantly, the fluid saturated rocks can be looked at as well in the frozen state. So next slide, please. So if we summarize with just a color, the type of samples that we can analyze with SEM and EDS, is you can see the solid color is more to the top of the triangle towards the solids, but there is a faded colors in the rest of the triangles just to show that we can actually analyze anything as long as it is in a frozen state. I will pass you over now to my colleague Jean Robertson, who will give you the explanation of the FTIR analysis.
Can I just, you can hear me okay? If anybody's having any issues, if you could just pop it in the chat so that we can pick up on it and hopefully get sorted out. As Evelyne said, I'm Jean Robertson and I head up the Fourier Transform InfraRed or FTIR analysis at the Institute. And pictured here is our laboratory with the FTIR spectrometer that we have, which is a Bruker Vertex 70. We also have an FTIR microscope attached, which allows us to analyze smaller samples. And in the middle, you'll see our sampling accessory that we use to put samples on directly. Anyway, but first of all, we'll start off. Next slide, please. Just start off by thinking about why we would use infrared radiation for analysis. So essentially, we're taking infrared radiation, which is at the red end of the spectrum, or just beyond the red end of the spectrum, which is where the name infrared comes from. And most people will be familiar with that as heat radiation. And that type of radiation is absorbed by a sample at specific frequencies depending on what the chemical composition of the sample is. So although it's not seeing in the way that we do with visible light, it does still allow us to see what something's made up of. For example, you could have a white powder, which could be anything from a drug like cocaine or something to something like limestone, and it may look very similar, but with the FTIR we'll very quickly be able to establish what type of material it is. And that's because the infrared produces a chemical fingerprint or profile, which we call an infrared spectrum or IR spectrum. And that shows us both organic and inorganic components. So very useful for establishing, as Evelyne said before, we can establish actual compounds which are present in a sample. Next, please. So to make our infrared spectrum, as I say, we use the FTIR spectrometer, and this schematic is showing how it works. Essentially, you have a source of your infrared radiation, which is split by a beam splitter, put onto mirrors which recombine and then go into the sample, pass through the sample. Once the infrared beam has passed through the sample, then we use a detector so that we can work out which of the frequencies have been absorbed. And initially it comes through as an interferogram where all the frequencies are shown together. And then the Fourier transform part is a mathematical equation to convert that into a form which is more usable for us, which is a form that we see here, the IR spectrum, where we see bands which are at different frequencies. The axis along the bottom says wave numbers, which is a pseudo frequency, and the mid-infrared, which is where we normally work, works from 4,000 to 300, about 300 wave numbers. And each of the peaks at the top, we see transmittance of 100%. That means that your sample is not absorbing radiation at that point. And then you can see the peaks pointing down at the frequencies where our radiation is being absorbed. Next, please. So just having another quick look back at how we actually arrive at this spectrum, as I say, the vibrational frequencies of molecules lie in the infrared region, and that's why they absorb light in that region. So looking at the very simple molecule of water, we have an oxygen atom with two hydrogens attached. Now that could be vibrating in different ways. The bonds can be stretching, and they can be stretching in the same direction at the same time, which is our symmetric stretching. We could have anti-symmetric stretching, where one bond is stretching and the other is compressing. Or we could have bending, where the bonds are bending from side to side. And each of these has a different frequency which will appear in our spectrum. And by identifying each of these frequencies, it'll help us to work out what the thing that we're looking at is. Next, please. So the spectrum, as I say, of water is very simple. When you move over to looking at more complex entities or compounds, you can get a range of different bands which will come from the different parts of the molecule. So for example, here we're looking at a spectrum of calcium naphthenate, which is something many of you may have come across before, blocking things. And we can see here that at the area just below 3000 is where we're seeing CH bonds, and we can see there's a lot of CH2 bonds. So those bands, that frequencies correspond to CH2, which tells us we've got long carbon chains present. And then further down, we see the bands that relate to the carboxyl, which are within the compound. So we get a complex mixture, and by a combination of first principles of knowing where we see bands for different things and expertise at comparing to spectral libraries, we can look at a spectrum like this and decide what type of material we've got present. Next, please. So the FTIR, the capabilities of it are largely qualitative, and it's an excellent technique for doing a rapid preliminary compositional analysis. So if you have some material, you've got no idea where it's formed, where it's come from, what type of thing it is, and for example, the sludges can be widely varying, then we can do an analysis of that and work out that, and it may be that we then pass it on to other techniques to do things in more detail. For example, if there was crystalline material present, we might ask Steve at the XRD, or if we need elemental analysis, we might ask Evelyne to do that. It's applicable to both crystalline and amorphous materials, which makes it very useful. And also very useful is the fact that it can be done for a very wide range of organic and inorganic samples, except it doesn't work for simple ionic salts. Having said that, hydrated salts are detectable because of the spectrum of the water attached to it, as we saw, and that will vary depending on the salt, and we can actually sometimes identify the salts just from the water associated with it. It can be used quantitatively, and we do oil and water analysis, and calibrations can be developed for specific systems where you have known spectra associated with measured parameters, and you develop a calibration, which then allows you to predict it for unknown samples. And as I say, but this has to be set up for any specific system. The sample types are, again, wide-ranging, solid, semi-solid and liquid, and it's also very useful for gas samples. Although we don't routinely run them here, this could easily be set up if anybody had something that they wanted to be analysed, like emissions or that type of thing. And the sample size is also quite small. We can use samples generally less than 1 milligram, but we also say that for tiny particles, if we can actually pick them up and get them onto the sampling area, we can usually get a spectrum. So it's always worth checking with us as to whether we can actually analyse what you have. Next, please. So when you look at the triangle in the same way as we did for the SEM EDS, you can see that the FTIR covers really all the different areas, from the solids, oils, waters. Water itself is not good to do, but we can dry down and find out things that are present in it. And so, yeah, we can cover a very wide range, and even more than's actually listed here, but this gives you an idea. Next, please. So what that means is, in terms of our triangle of samples, essentially anything within that triangle, any range of things, should be suitable for FTIR analysis. And it's always worth asking us if you have a sample. I'll now pass over to my colleague Steve Hillier, who'll talk to you about the XRPD.
Thank you very much, Jean, and good afternoon to everyone. Okay, well, I'm going to talk about the final one, if you like, of the trinity of the kind of 3 key complementary techniques for problem samples. And this first slide just shows an image of one of the 3 XRD instruments that we're fortunate to have at the James Hutton Institute. And essentially, with X-ray diffraction, we irradiate the specimen in a form of a powder with a beam of X-rays, and we obtain information from the interaction of the X-rays with that specimen. Next slide, please. So here's a schematic of what a modern X-ray diffraction instrument looks like. We've got an X-ray source, which usually gives a monochromatic radiation, typically copper or cobalt, just generated in an X-ray tube. We've got a detector, and in modern instruments, both of those rotate through the same angle theta, and we essentially plot the output in terms of 2 theta. The reason we use a powder specimen is so that we have many crystals in all orientations. Ideally, it would be what we call a random powder, and so that just increases the chance that some crystals will be in the correct orientation to diffract. And to diffract, what the crystals have to do in terms of the radiation they're being irradiated with is satisfy the Bragg equation. And the Bragg equation is satisfied when we have constructive interference. Otherwise, there's just kind of scattering in all directions. So one of the biggest mistakes that can be made actually is not to mill the sample to a fine enough powder, because that fine powder, the more we can kind of generate billions of little crystals by grinding them up, we'll get a much better chance of getting a good diffraction pattern. The Bragg equation is a kind of simplified interpretation of X-ray diffraction, but essentially it relates a d-spacing, which is a spacing in a crystal. You can see some crystals down there with planes of atoms, to the wavelength that's being used in the experiment. To say when that equation is satisfied, that's when we get peaks in our diffraction pattern, which is typically plotted in terms of 2 theta. Next slide, please. So here's an example of a diffraction pattern of common salt. If we take a pure substance like sodium chloride, we can see how the peak positions in terms of 2 theta or D spacing, which I've also laid on here, relate to the crystal structure of sodium chloride. I'm sure we've all seen these kind of cubes of sodium chloride, common salt. The crystal structure reflects that that kind of cubic form. And with X-ray diffraction, we don't just get information on the structure, but we also get some information on the composition. And very kind of simply put, the peak positions in this X-ray diffraction pattern relate to the kind of the crystal lattice structure, whereas their intensities, or heights, if you like, or peak areas, depending on how we measure them, that relates to the different types of atoms and their positions. We tend to label them with a D spacing, which is the kind of fundamental spacing in the crystal structure. And also sometimes they're labeled with these indices in parentheses here, which are called Miller indices. So like the 111 peak has a D spacing of 3.2 angstroms, for example. And a diffraction pattern is fundamentally a direct fingerprint of what that substance is. It is sodium chloride in this instance because it has this diffraction pattern. It cannot be anything else. I always actually like to refer to the fact that NASA have sent an X-ray diffraction instrument to Mars. And the reason they did that is because X-ray diffraction is so fundamental in actually telling you what something is. The properties of chemical compounds obviously depend on their structure and composition as well. So if a chemical analysis identified a substance as containing, for example, just iron and oxygen, we wouldn't necessarily know exactly what it is. We might be left wondering which of a half a dozen iron oxides, for example, it might be. But XRG would tell us exactly which one it is. Very, very fundamental measurement technique, if you like, or measurement probe. Next slide, please. So here's an example of an X-ray powder diffraction pattern that we might obtain in the laboratory. Again, it's a series of peaks plotted against a 2 theta scale. I've put the Y scale on a square root scale on the side there, just to emphasize some of the smaller peaks. That's often a useful way to look at them. And the line going along the bottom there is just kind of some way of sort of defining roughly where the background to that pattern is. It's typically the peaks that we're interested in. And keep in mind that most of the samples we receive are mixtures of different compounds, and the diffraction pattern then that we obtain is a sum of the component patterns of the individual components. So the process of identification here typically involves matching patterns from databases or monographs or based on experience with the observed pattern. And we're fortunate enough to have the latest tools from the International Center for Diffraction Data, the so-called powder diffraction file databases, and they've got the organic and the inorganic to help us in this kind of identification process. Next slide, please. Now, the identification process typically is a kind of iterative process. You identify some peaks. Often you recognize some of these compounds because you've seen them so often before, and then we look to see, well, what peaks are left as we kind of work through this process. It's assisted by various pieces of software, although when we've seen round robins on this process, it's very clear that the experience of the analyst is probably the most important factor in getting a kind of reliable and an accurate identification. The software simply makes suggestions, and you kind of have to sift them out with common sense and experience. Next slide, please. And then here's the final kind of, final identification of this particular material here. We've matched the D spacings. I've labeled some of them here in angstroms, but in the match process, we also try to match the relative peak intensities for a given different phase or mineral or whatever it is. And the final solution to this particular sample here has 5 different phases matched. You can see there's some gibbsite and aluminium oxide, some hematite, which is an iron oxide, a little bit of quartz, some goethite, another form of iron oxide, and some anatase in this sample. 1 or 2 small peaks still remaining, and there's probably some traces of other materials in here. The detection limit of XRD will probably, nominally be somewhere around about the 1% level. It can be a lot lower if you take particular care to do things carefully. Next slide, please. So in terms of the kind of overall capabilities of X-ray powder diffraction, most often we're using it in a kind of qualitative way. So just for the identification, mainly of crystalline compounds, as I mentioned earlier on there, it's a definitive technique. Sodium chloride is sodium chloride because it has that diffraction pattern. We can also identify the presence of amorphous compounds, and in certain cases we can quantify them, but XRD is probably not the strongest technique for that. Clay minerals in particular are often only identifiable by X-ray powder diffraction because they often consist of mixed layers. We can also do quantitative analysis. We can do some pretty highly accurate quantitative analysis. It is probably unsurpassed when materials that you're looking at of a fine particle size, and for example, you can't really see what they are under the microscope because they're so finely mixed together. In terms of sample size, again, like infrared spectroscopy, if you can see it, we can work with several milligrams, but typically we can only just do an identification then, and even sometimes then we might be stretched. But if you want quantification, we tend to need a lot more material, and that's primarily because good quantification needs a lot of care with sample preparation when you prepare your specimen. Next slide, please. So here we are with XRD very much at the kind of top of the triangle. The things that we might look at are minerals, drill cuttings, scales, soils, which is a lot of history in looking at the minerals in soils. Clay minerals, a lot of history on that too. Metals, corrosion products, polymers, which tend to give sort of a diffraction pattern somewhere between crystalline and amorphous, sometimes often referred to as paracrystalline, and ceramics. And in fact, most materials that are solid, we can deal with. Next slide, please. And so to kind of join together with the other kind of techniques that you've had, you can see very much X-ray powder diffraction is typically dealing with solids. So we've just kind of colored in the top of the triangle here. Next slide, please. So to summarize, here are the 3 techniques that we've presented. Electron microscopy that gives you information mainly on morphology, but also chemical composition, and also the chemical composition of individual particles. You can actually see what you're analyzing chemically and how it occurs spatially in a sample. X-ray powder diffraction, which I just discussed, which is the kind of definitive technique for the identification and also very good for quantification. And then FTIR, which is the kind of, almost the jack of all trades, if you like. It can do all kinds of different samples. It's mainly showing you information on chemical bonds and so on. So I've spoken about those 3 techniques, and they all bring a different perspective to the table. But probably the most important thing to take away is that they're all complementary. We haven't focused on any particular examples today. That might come as a subject of another webinar, but essentially to illustrate the principle, if you were struggling to identify a compound by XRD, we might go along to Evelyne and see if we can get some chemical data from electron microscopy that would then narrow down or constrain the search match procedure, and we might be able to identify the compound with much more confidence. Or a sample might be sent in for X-ray diffraction, for example, and it turns out just to be an amorphous pattern, which can be rather difficult to identify precisely by XRD. So we would go through and pass that to IR, where they may be able to see exactly what kind of functional groups it has present and be able to identify it straight away. And that then also might be combined with supplementary chemical information just to confirm that identification. But That said, you can have all these techniques in your laboratory, but at the very heart of this kind of collaboration between these techniques really is the experience of our staff, not just in using these techniques, but knowing when to call upon another technique. They're all largely interpretive techniques as well. So as mentioned at the beginning, your question and the context about your sample is absolutely key. You might send us something, and if we know what question you're trying to answer by sending us that sample, that can be absolutely key. Next slide, please. So I'll finish up with a list of our teams. We're fortunate to have quite large teams of people working in and across these three areas, and amongst them there's a massive wealth of accumulated experience of skill and expertise. And at the end of the day, I think if you're sending samples to us, this really is the key benefit of asking us to look at your problem samples. It's the experience of our staff. So I'll hand over now. I think I'll stop there and hand over to Gareth, I think, to summarize.
Okay, thank you very much, everybody, for a very interesting presentation. I have actually seen that a couple of times now, and I'm learning each time I see it. I'm picking up things. I think what it really does emphasize is the fact that you do need some expertise and experience in getting useful information from these techniques. We have some questions, some submitted before the webinar took place, and there's one that's appeared on the screen. If you have any more questions, please submit them. We can ask them now. I have a question for I think this is for all of the panelists. Could you tell us what sample preparation is required prior to analysis for each technique? Can we start with Evelyne?
Yeah, so preparation really depends on the type of sample that you're sending. A rock samples would have, for instance, to get cleaned first if there is any oil into it, just to make sure that we've got a dry sample, unless we want to analyze it in cryo, obviously. But we will try to get a fresh fracture just to really see these minerals in pristine condition. But you may send some membrane sample, and we just want to prepare it just by taking a little piece and put it without disturbing it as little as possible straight under the electron beam. There is so many different types of samples. It's really up to the operator just to decide what is going to be happening. Obviously, some of the samples for dry material need to be kind of conductive, and we have ways of making those samples conductive by coating them if it is necessary. The reason for coating is that the electrons are taken away from the sample, and we can get a proper image. I think there is so much to elaborate on that. It really is depending on the type of sample we're getting, from rock to powder or sludges.
Okay, thanks for that, Evelyne. Jean, have you got something to say on that?
Yes, I mean, again, it's like Evelyne said, it's a lot to do with the type of sample and what you're trying to get out of the, again, what the question is you're addressing. We always run get an IR spectrum of the sample as received, just to firstly get an idea of what we're trying to do and check that we don't miss anything or we don't lose anything through our preparation. But the preparation can range from things like separating it out into different fractions, like soluble fractions perhaps for separating out inorganics and organics, washing with water, drying down. Again, as Evelyne said, there's a great deal. A great deal depends firstly on the sample, the type of the sample, and also on the type of information that you're getting out of it. And I have to say, this is actually, as she said again, key to getting the right results, because if you don't get your prep right, you may not, you could do something as received, and all that you will see is the hydrocarbons and the oil, and you say this is just oil. It might be full of a mineral or something in the form of a sludge. None of that will be seen unless you separate it out into the fractions. So yeah, I mean, as Evelyne says, very much sample dependent, and a range of things which we judge when we see the sample or when we know what it is that we're looking for.
Okay, thanks, Jean. Steve, do you want to add something?
Yes, I mean, essentially everything that's been said there already applies to X-ray diffraction in many ways. There's absolutely no doubt that sample preparation is the key. You can have the most sophisticated instrument, available, but if you don't get the sample preparation right, it doesn't make a lot of difference. So effort spent there is absolutely key, and that's where our experience comes in for sure. For X-ray powder diffraction, there's two key things that you have to get right. You firstly want to try and get as random a powder specimen as possible when you're dealing with identification and quantification. We use a method called spray drying for many rock samples and things that we do for that. When you're dealing with smaller samples where it's just identification, you often can't do that. So finely milling your sample as fine as you can get it to ensure you've got these billions of crystallites is about the best thing you can do. And as I mentioned in my presentation, it's the biggest mistake that novices often make, is not to mill the sample as fine as possible. You have to be careful when you do that as well, so that you don't damage the sample. Particle size and texture, the two key things you have to try and control with X-ray powder diffraction. So that's what you have to get right.
Okay, thanks for that, Steve. I'll take some questions from the floor now. This is a question for Jean. Can you please elaborate on how FTIR can be used on inorganic materials?
Well, the thing is that you get in the same way that you get a pattern from the organics. It depends on what you've got, the bonds that you've got connecting the inorganics. So, for example, for carbonates, you've got within the carbonate entity, you've got carbon-oxygen bonds, and again, so that will give you a pattern. And it's the same for, as I say, within the clay minerals, you'll have OH bonds, which you can relate to the exact type of mineral. So most inorganics, if they've got a sort of bonding system, something like sulfate, you've got sulfur oxygen bonds in it. It's not like a simple ionic where there's no where it's all kind of electrostatic. So yeah, for inorganics, you get patterns very much like the organic patterns. And so, for example, for carbonates, you can determine which carbonate it is. You can determine whether it's calcite, whether even if it's calcium carbonate, whether it's calcite, whether it's aragonite, or or whether it's a different or dolomite, which has got magnesium in it as well. So the bands that I talked about and I showed for calcium naphthenate, you get similar patterns for almost all inorganics as well. And as I say, with the right spectral libraries and knowledge, it's possible to interpret them and identify them that way. Thank you.
Okay, thanks, Jean. That was from Andy Gale. Does that answer your question, Andy? I don't know if you can unmute. Hi, Andy. Not hearing you. I think in the interest of time, I will move on to another question. A question from Kirsty. I assume this is for XRD. Are you able to take thin section of shell and look at a fracture structure, for instance, within that rock?
I think SEM. That will be for SEM.
Yeah, I'm going to say it may be SEM.
Yes, slip of the tongue there. Yeah, well, obviously we can look at anything there, and a thin section of shale, if it is embedded and flat, you just have to look at it. There is no reason why we wouldn't be able to look at the fracture structure in this case. Our system is a field emission SEM, so therefore we can actually look at very, very high magnifications. And yes, we have looked at shale surfaces. Depends what you're trying. I mean, at the moment there is some research being done for shale oil and all that, and you need to have a look at polished surfaces for it to find out where the kerogen is and all that. When you do a fresh fracture of shale, it's actually sometimes quite difficult to look at it, because each mineral, each clay mineral that is effectively laminated appear as almost as a fracture. So I think we would probably need to have a polished section there just to have a proper look at the fracture. But yeah, there is no reason why we wouldn't be able to do that.
Okay, thanks very much, Evelyne. Another question from Andy. Which of these techniques stroke sample preparations make the sample unusable again for analysis by another technique? Do you mean unusable or usable, Andy?
Well, I think we can still kind of reply generally. Yeah. SEM tends to be considered as non-destructive. However, if we have coated the sample with a metal like gold or platinum or anything like that, then it has changed the material in some ways. So there are some samples that can be taken off from the SEM and put it straight onto the FTIR stage, for instance, and vice versa. We have taken samples, tiny little samples from the FTIR stage onto the SEM because we had nothing else. As far as XRD is concerned, I'll let Steve reply on that.
Yeah, I think if the question is, can samples be shared around different techniques? I mean, usually they can. You might have to think carefully about the order in which you do things, because XRD, for example, typically wants the sample in a powder form. So if we only had a small amount of a sandstone sample, for example, and somebody wanted to look at it by electron microscopy, then that would have to be done first. But then the sample could be, potentially powdered afterwards, and we could look at the minerals in it by X-ray diffraction, and the powder would also be suitable for IR. So I think in most cases it's rare that the use of one technique, totally it eliminates the use of another, but you may have to think about the order in which you do them.
Okay, thanks, Steve.
Could I just add one
Yep.
more thing, is that because for some of the techniques like FTIR and sometimes depending on what you're doing with the XRPD but also the SEM, we often use a very, very tiny amount. So the amount of samples supplied by the customers is usually quite a lot more than that. So even if we want to pass material on for other techniques, for example, some of the chemical techniques, it's unusual unless it's a very, very tiny sample for that to not to be possible. So as Steve said, yeah, as long as we think it through, we can usually do a large number of different analysis on the one sample.
Okay, thanks everybody. Another question for Jean. FTIR has been used in analysis of vegetable oils, identifying adulteration, measuring degree of saturation, breakdown, etc. Do you have experience of using it with vegetable oil samples?
Not specifically we haven't specifically studied that sort of thing, but there's no reason that that we couldn't. I mean, we have done vegetable oils for in different ways, looking at each of the different ones has a different signature and different properties. So we haven't specifically done that kind of studies, but we've done a lot of things and studies on other types of compounds where there is a kind of a range of saturation and different things like that. So again, it would just be a case of talking to us about what you required, and then yeah, I'm sure we could work something out that was suitable.
Thank you very much, Jean. A question from Ramesh. Could you explain what is a suitable and accurate instrument for determining organic carbon content in classic sedimentary rocks? Does anybody want to pick up on that?
Certainly, SEM is not suitable for that. SEM will not measure and really see the organic carbon compared to any other kind of type of carbon.
Yeah, I can pick up on that. I mean, we do have instruments in the Institute. I can't think of the name of it just now, but it's a pyrolysis technique is usually what's used.
Is that?
Yeah, Jason typically does it, doesn't he? I mean, the complication you'll get with sedimentary rocks is that often you'll have, carbonates as well as organic carbon. So you have to very carefully, remove the carbonates and reanalyze in order to get to the organic carbon content. But I think typically the industry standard would be various pyrolysis, techniques, thermal techniques.
Yeah, if you want probably a bit more information on that, the person to perhaps get in touch with is Dr. Jason Owen. His email address will be the same as ours, except just Jason Owen in front of it, and then at hutton.ac.uk. He'll be able to help on that.
Okay. Can I just say that although the FTIR probably wouldn't be in a position to quantify that, if you wanted to look at organic carbon within a system or the type of material it is, the FTIR would be useful for that, and it could be used in conjunction with, for example, Jason's technique.
Okay, thanks Jane. Another question, not quite sure who this is for. Is it possible when we get a fiber size and its distribution and fiber orientation, also distribution? Is anybody able to help us on that?
I don't think that's something that we do really. I mean, Evelyne could obviously look at, fibrous materials under the electron microscopy, but there are some diffraction techniques that do this kind of thing, but it's not something that we do here.
Yeah, well, I'll add up something on that. Is that without knowing exactly, again, that's a really good example of context. Why do we want to know that? And we might be able to help, but we need to know a little bit more. But certainly SEM can visualize these fibers and give some information on their sizes and their orientation, if their orientation is in situ. If we don't have to prepare them by just spreading them onto an SEM stub, for instance. So by knowing a little bit more of why you would want to know this, we may be able to help.
Okay, thank you, everybody. Another question for Evelyne. This came in prior to the webinar. Please, can you throw some light on how SEM can be used in kimberlite indicator mineral grains?
Right. So this is a technique that has been developed over the past 20, 30 years. It started in Australia, really, for mining. And it is in terms of kimberlite, what you want to try and find out is the mineral assemblage to determine whether the hardness, the grindability, the mineral abundance, and it's eventually the diamond grade and the recovery of the diamond may be determined, but that has to be done in a quantitative manner. So it is an SEM and EDS based technique, but it is based on an automated technique, and it's done with the type of equipment that's called ChemScan. Or there is another one called a mineral liberation, kind of MLA, Mineral Liberation Association or something like that. And basically you need a system that is rapid and can do vast amount of different samples in a very short time. So it's an automated technique that requires, we have 2 EDS detectors on our system, and I'm very, very pleased with that because it does help a lot. But these techniques require 4 EDS detectors so that the signals is much acquired much faster, and it does a quantification, basically statistical quantification of the different mineral assemblage. So it is possible by SEM, an SEM technique. We cannot do it here, that's for sure.
Okay, thanks, Evelyne. I think we've probably got time for one more question, and then perhaps we need to wrap up. This is a question for Steve. Can you use XRD to do quantitative analysis of corrosion products?
Yeah, the answer would be yes. Again, it depends very much on the amount of sample material that you have. That might limit your sample preparation and then what techniques you could use. I mean, most of the samples we get in of corrosion products, you know, most people just want an identification, and we can do a semi-quantitative determination of abundances. If the corrosion products are quite exotic, then it can become more difficult. But even some very exotic samples, sometimes if quantification is an essential element, can be done by various diffraction methods. The key thing with X-ray diffraction is that the peak intensities, the peak heights, if you like, or the peak areas are proportional to concentration. So there's often a way to get to a kind of quantitative analysis of materials like that.
Okay. Thank you, everybody, then, for your presentations, and thank you for the answers that were given there, and thank you, attendees, for the questions. I think we'll need to start wrapping up there. Contact details for the presenters will be sent to you for any of the topics you've heard today, and for myself for anything that you've not but would like to inquire about. Please get in touch with me, Gareth Newman.